In this part of lecture, we'll learn the steps of Bode plot construction, but this is different from the previous one. Previous one, we use the equation, the calculation of magnetic phase of some complex variable quantity. We are not using that anymore. So you will be hearing the term asymptotic a lot here. Bode plot construction, or more specifically asymptotic construction of Bode plot, or asymptotic analysis of frequency response. This is very important, okay? Let's talk about the Bode plot construction or asymptotic construction of Bode plot. Assume this is the TS of the TS is the transfer function. We want to sketch the frequency response of this transfer function. It has constant, it has this term, okay? If this is positive, then it comes in the denominator and it becomes integrator. And if this is negative, it goes up, S goes upstairs and becomes differentiation, okay? And it has a single pole. This is called the single pole. This is called the single zero. And this is called the double pole and double zero, okay? So we'll be talking about the Bode plot of this one, this one, this one, this one, this one, this individually, okay? This individual fact called I don't know, they call it what, but I'm calling this as the multiplication factor. So transfer function is factorized into the multiplication factor form, and each of this 1 plus s divided by something, this form is called frequency response form. Previously I was calling it standard form. Some guy complained why that is standard. So okay, then I call it frequency response form, okay? So TS is only consists of this 1, 2, 3, 4, 5, 6 terms. Why is that? Why we only consider these 5 terms? How about the cubic terms? Suppose you have some S cubic terms involved with S cubic. You are not considering that because this basic construction rule for the Bode plot using the asymptote is only applicable, only this 6 element. If you have third order term somewhere here, you must approximate that. You must factorize that into single order term and the second order term. Okay? At least you should have approximation for that to use this technique. Okay? There's no general rule constructing the S cubic order term. Okay? It's impossible. Then what you need to do is you should split them into 2 terms. One is a single order term and the other one is a second order term. Okay? This splitting is always possible if you choose the value of your circuit variable wisely. Suppose you have this kind of circuit. This is a 2-stage filter like this. You select this 10 microhenry and you select this 15 microhenry. You select this 10 microfarad and 15 microfarad. That it is almost impossible to split into these things. This is first order tester, first order equation. Then you want to split into 2 second order equations. But this is impossible to do that because this circuit component is almost the same. Okay, so to have this, you have separate the time constant of circuit in advance. Right? Suppose you increase this. Okay, you don't want to increase something, so you decrease this. .1 microhenry, and you decrease this 0.1 microfarad. This is just illustration, so I can use whatever number I want to use. So I use this strange number. Oh, this is bothering. Okay, so there are huge difference, more than 10 times difference, about 10 times difference between this value and this value, this value and this value. Then this is a first order equation, but it will be separated into two second order terms very easily. So this element and this element, they combine together to form first double pole here. And this they combine. It does not depend on the location of this element. The value is important. So smaller ones, they come together, and the larger one is they merge together. Then you will have this kind of frequency response. So this first one is coming from 1 over square root. This larger one, microhenry, and this one is 15 microfarad, and this one is this double pole is coming from the smaller guys. And okay, and the order of this is in the spatial order. Order in space is not important. Okay, location is not important. Their values are important. If you select this value in this manner, then you can have this. That means this term, this will be split. Okay, this is this one, is double pole. Then there is a one quadratic term here, another quadratic term here, and they can split this with negligible errors. Okay, so this is the trick. When you are designing, then you have this. Suppose you want some attenuation. This is very good. This is a huge attenuation. This is -4 dB attenuation. Another -4. So total is -8 dB attenuation. It's much better than using. Combine this together, and you have a FET inductor and the FET capacitor. You used about the same money, but performance of that filter is very, very bad compared with this one. Okay? So always this is the good approach. When you are doing this, use the component value wisely. So later on you can easily analyze this. If you put everything together, you cannot do anything. Maybe the PSPI simulation, some simulation is available, but that is just garbage. Does not provide any insight for the design improvement or for the control design. Okay, so this is engineering approach. It is called design-oriented analysis. Design-oriented design or design-oriented analysis. Okay, so don't try to use the exact equation. Okay, try to use this approach and try to use your insight. That helps you to analyze something and extremely useful for the design something. Okay, so this is the message I want to convey. So transfer function is factorized. If possible, approximately factorized. This can be done always, okay, by selecting in this manner. And general rule for the factorizing polynomial into smaller order polynomials is that technique is provided by the Erickson's book, Bob Erickson. He provides some mathematical things. Okay, so if you go that book, you can factorize any polynomial. Okay, with minimum error. Okay. So way of constructing, this is the huge equation. Way of constructing this is very complicated. Then you factorize that TS into this form, this multiplication factor forms, and draw the asymptotic plot of each term individually and combine them together. And combining them is very natural and very easy and very easily done graphically. Okay, that is the one best advantage of Bode plot. Okay, if you use some other plot, there is a other plot, polar plot or Nichols plot, that feature is gone. All right. So if you have some complicated transfer function, try to factorize this, and in most cases they are already factorized. If you analyze the circuit, they are usually factorized because of the structure of the circuit. If you use OPM compensation, they will be factorized these false order terms, zeros and poles naturally. Okay, we went through that, right? Because of the characteristic of poles and zeros, it is factorized already. Okay, and otherwise, then you can approximately factorize this. So assume you factorize this into form, and let's go through the one by one. This is very easy. So this is a constant. If constant is this one, 20 log k, 20 log k. If this is a positive, the phase remains 0. If this negative, phase becomes this minus 180 degree. But the 180 degree is the same as minus 180 degree because it's rotating. But use this one. Okay. If this phase is coming from 0, then you go up. Otherwise, you go down. Okay. They need together because this vector is rotating. And one thing I want to say is this one. Suppose you have this kind of frequency response simulated, measured with something. Then probably this is plus 1 slope, 20 dB per decade, minus 1 slope, minus 20 dB per decade. Then phase here is 90. Okay. This plus 1 slope means phase is 90. So phase is staying 90, and this is the phase of minus 90 degree phase, minus 90 degree phase. Then what happened in the middle? It will go down. It must go down. Okay? So it goes down, and at this frequency, where this frequency response to the peak value, phase is, this should be 0. Okay? So horizontal line phase of horizontal line is 0. If you have some complicated this frequency response at each peak of these waveforms, phase should be 0. Okay, that is also important, and this is useful for the sum analysis. Okay. All right, and the next one is this S is coming in the denominator. This is called integration. If S is 1, first order is simple integration. If S square is here, it's called double integration. So this is double integration. And this is simple integration. And you evaluate the magnitude and the phase. J is in the denominator, so phase remains this minus 90 degree. And omega is in the denominator. So if you increase omega 10 times, then this value becomes 1 divided by 10, 1/10. Okay? This is what? This is minus 20 dB per decade slope. Is obvious from this structure. So it starts from 0 and it goes down like this. And the slope is minus 20 dB per decade, or we use number minus 1 later on. Okay? And this frequency is Ki. When this omega is Ki, this becomes 1, which is 0 dB. So 0 dB crossover frequency is sometimes important. You should know that. Okay? That frequency is given by this value, and this is omega. You cannot plot 0 frequency here. Okay? Because 1/10 forever. This is not a 0. You cannot draw this line. It's not 0. It's move this direction infinitely, then you will have 0. Okay? And for this case, this slope becomes steeper, because if you increase this 10 times, then whole thing will be decreased by 1 divided by 100. So it is minus 40 dB per decade, and this 0 dB crossover frequency is, if this value is this one, and they scaled and they cancel and becomes 1. Okay? So This 0 dB line is here. 0 dB line here. All right, okay. And this is, S is in the numerator. This is called differentiation. With this is the single differentiation with S squared as the double differentiation. And opposite to the integration case, this is increasing. You increase this 10 times, then this will be increased by 20 dB, right? Because it is in the upstairs. Okay, this slope and this omega is here. Then this becomes 1, and that is 0 dB. Crossover frequency is located here. This is, it has steeper rising slope, 40 dB per decade, or plus 2. This one is plus 1 slope, so this is 0 dB. Okay, J is in here, so phase is 90 degree, and J squared is minus, we have minus here, but minus 180 is same as 180. Then use this number. If something start from the numerator, then start go up. Okay, something comes from the denominator, go down. That is the general convention of plotting this. Okay, so here this is increased by 10 times. Then the magnitude of the whole thing increased 100 times squared. Okay, all right. And this is a single pole. This single pole. Previously, we used the equation of magnitude and the equation of phase. That is the exact analysis, which is less useful than this one. This is asymptotic plot or asymptotic analysis. So we divide this frequency range into 3 subdivisions. Okay, S is J omega, and omega is less than omega P. Omega comes before this pole frequency omega P. Then this term is very small because this is smaller than this one. So this can be ignored and it becomes 1. Okay, at this frequency omega P, they remain the same, so they cancel. And this is the exact expression when this omega is much larger than omega P. Then this is very large in magnitude. So you ignore this. Then you goes up. This guy go up is here. So this is what? This is integration passing through 0 dB line at this frequency. Okay. So draw this. One asymptote is here. This is 1. Okay. This is valid up to this frequency. So you have this part, and at high frequency you have this. You have this. Okay. So this line segment is passing through this point. But this is valid up to this frequency. The connection of these two asymptotes provide you asymptotic plot of Bode plot of frequency response representation of this first order pole exact plot as shown here. So we have 3 dB difference as predicted. Okay, and the phase is like this. So phase here is 0 degree, and here is minus 9 degree. They decrease linearly. Okay, this is the asymptotic plot. So we have some error. This asymptotic slope is minus 45 degree per decade. And here we have some error. And we know this error. There should be error. There should be error. Okay. But at this frequency, the magnitude error is the maximum, which is 3 dB. And the phase error is 0. This is the exact point. This is the exact point. Exact value. This is single integration passing through 0 dB line at omega p. All right. So this is the way of plotting this. And from this asymptotic plot, you smoothly connect this and passing 3 dB line at here. Then people cannot tell the difference between this manual sketch and the computer generated plot. They are almost the same. So this is the way. Okay. Again, I said this is 3 dB frequency, omega p. Corner frequency, breakover frequency, pole frequency. They mean the same thing. Okay. So single pole and the single zero is opposite to the pole. So everything remains same, but at this is the exact value at high frequencies. This one remains, and this is what? This is differentiation passing through this omega g frequency, this frequency. So 0 dB line is this part, and this is this one. You connect them, and smoothly connect through this 3 dB line. Then you will have exact response, and the phase remain the same. And this at this frequency, as phase is 45 degree, it start out from the 0 degree and converge to the 90 degree. It never increase further. Okay, it converges to this value, right? Double pole frequency. Previously, we went through some equations to plot this. Okay, but just do this. Divide this frequency into subdivisions. Okay, so this is the boundary between our division. So before this frequency, then this is very small. This omega is small compared to this. Then they are gone, and it becomes 1. So it starts from this one. Okay, and at this frequency, this is omega naught. Then this cancel, this cancel. And they cancel, it remains here, it goes up to upstairs. You have this, okay? So phase is exactly 90 degree, and this peak value, this phase and magnitude is 20 log P, not 0 dB. So we have 20 log P peaking at this frequency. Phase is 0 because number 1 has 0 degree phase, and this one has minus, so phase changes from 0 to minus 180, and there is a transition at this point, and at this frequency, phase exactly becomes minus 90 degree. Okay, so this is what is double pole. This is double pole, but around this frequency range, the characteristic depends on the value of the QP. So with larger QP, the peaking increase, okay, proportional to QP, it is increasing, and this slope becomes steeper as larger as the QP increase. Right. So actually, the exact calculation of magnitude of phase is not necessary. Okay, that is a kind of overkill. We don't need that. And based on this, with this knowledge, this is the frequency response or Bode plot can be sketched with good accuracy. Okay, estimated the peaking and everything. So this is the approach we will take. And this is double zero. Double zero is in here, everything is opposite to the previous case. So we have this, and we have this dipping, right? So this zero is creating a dipping, and the pole is generating a peaking, like that, okay? The phase is 0, and this phase is minus 180, but this comes from this numerator. So we use number 180 here. At this frequency, it increases exactly to 90 degree phase. So this is the exact one, and this is what double integration. This double integration and double differentiation, and it passes this omega naught here. Okay, so this part of this asymptote is this one, and remaining part is this. Okay, and if you have some Q value, then increase this and smoothly connect them. That is more than enough for any practical analysis. Okay, plotting the exact curve is nothing. Don't do that. Okay, just know this and connect this, and the deviation starts from 0.3 of omega naught, and deviation ends at the 3 times of omega naught. Okay, generally, and the phase is usually phase is not important. Okay, but phase is changing. It depends. This actual slope depends on value of the Q. There is a functional relationship between this slope and Q, but let's use this, okay? Don't pay attention to that. There are some guys who developed the exact relationship. And previously we have plus sign here. Now we have a minus sign, okay? And minus sign it came here. It located in downstairs, and it looks like this. This is called what? RHP4, okay? So this is S plane here. S plane here. This is sigma J omega, and usually pole appears here, okay? So this frequency is minus omega p, and sometimes pole appears here, omega p here, okay? So this is RHP, right-hand plane of S plane, and this is LHP, left-hand plane of S plane. So usually pole occurs here, okay? But in this case, pole occurs here. This one causes some problem. System is unstable initially, so you're not going to see this much because you are not dealing with unstable system. System itself is unstable, but it is very hard to stabilize this, so you are not dealing with that. Okay, so with this time domain, this response should contain term minus omega p t. This is increasing forever. Okay, so this increasing forever means unstable. Okay, with this you have this is called the natural mode, and you have a natural mode of something like this. Something like this, start from some value, indicates, so e to minus omega pt comes here. Okay, so it decays exponentially, fast, decays very fast. So this is a stable system, this is unstable system. Okay, so anyway, this is the unstable system, right? I think I told you this following things several times to my student. In the nature, okay, everything is stable. Suppose this something was unstable, so there is a rock on the ground or on the mountain, and rock looks like this, This is unstable. It balanced, okay, barely. So it's sitting like this. This is nearly unstable. Small winds will bring down this direction or this direction. So what you are seeing in the world, in the real world, unstable things are all destroyed or all moved to the delocated to the stable position. So what you are dealing with is mostly stable one. Okay. So anyway, this is the case. So you have RHP4. Then magnitude formula is this one. This one is same as the previous one, regular pole, but phase is we have minus sign here, and this guy is coming in front. Minus becomes positive one. So this magnitude wise, it is pole, like regular pole, but in terms of its phase, it is zero, not a pole. It's opposite. Okay. I have one more page, but it requires some time, so we stop here. Okay. All right. So you know the rules for the next week, and get prepared the midterm test in advance. Okay. Thank you for your attention. All right. We stop here.